Welcome back, pre-calculus students, and today we will go through chapter 5.2, exponential functions. So, what's an exponential function, you may ask? Well, it's a function of the form f of x equals k times a to the x power, and k is a constant, it doesn't change. A is also a constant, but it's called the base because it's going to be what the base of our exponent is raised to, and then x is the exponent, of course. And the exponent has to be bigger than 0, has to be positive. Not the exponent, the base. The base a has to be bigger than 0 and not equal to 1. You can see what happens if the base is 0 and 1, and you can explore that, why you would want that to be the case. But let's dive into an example. So g of x equals 2 to the power of x. One thing I want to note is in the last chapter we did polynomials, which had exponents, but the difference being those polynomials, the exponents were all numbers that stayed constant, whereas exponential functions, the exponent is the variable. The exponent is the part of the function that's going to change, and that's what makes the exponential function versus the polynomials that we saw in the last chapter. Alright, so the way I like to graph these, just pick a few simple points. So if I plug in 0, 2 to the 0 power is 1, and then if I plug in 1 for x, I get 2 out, and if I plug 2 in, I get 2 to the 2 power, which is 2 squared, which is 4, and then 2 to the 3rd power, when I plug in x is 3, is 8. Now let's get some negatives in there, like negative 1, 2 to the negative 1 power is really 1 over 2 to the 1 power, which is 1/2. And if I put in x is negative 2, I get 1 over 2 squared, which is 1/4. So then I connect them, and there's my exponential function. Great. One thing you should know is as x goes to infinity, that function goes off to infinity, and then as x goes to negative infinity, the function goes to 0. So let's look at an example where the base is less than 1. For example, what if it was 1/3? So h of x equals 1/3 is the base, and again, x is our exponent, our variable is in the exponent slot. Well, we'll just plug in some points. X is 0, out comes 1, x is negative 1, out comes 3, x is negative 2, out comes 9, x is 1, out comes 1/3, x is 2, out comes 1/9. So we go ahead and connect the dots, and we get that exponential function. So one thing you're going to notice is when the base is bigger than 1, you have what's called exponential growth, because as x gets larger, the function shoots off to infinity, and as x gets very, very, very large negative, it goes to 0. And the graph on the right is exponential decay. That's when the base is between 0 and 1, so it's like a fraction, for example 1/3, and it's going to go to 0 as x gets large and then go off to infinity as x goes to negative infinity on the left end of the graph. Alright, let's look at an example. Let's graph this exponential function, 2 to the x minus 4 power plus 2. Alright, so one thing I like to do when I'm graphing exponential functions is I like to get the asymptote down on the graph, right? So this one, on the right end, it goes off to infinity because like when x is huge, it's 2 to the huge plus 2, which is huge. But on the very large negative, let's see what we get. So limit as x goes to negative infinity, 2 to the x minus 4 plus 2. Well, when x is negative infinity, it's going to be 2 to the negative huge power plus 2, which I can rewrite as 1 over 2 to the huge power plus 2. And 1 over 2 to the huge is going to be basically 0. So we find out that as x goes to negative infinity, in other words, on the very left-hand side of our graph, the function approaches 2. So that gives us a horizontal asymptote to write on there. Okay. And you may have learned how to find asymptotes without using limits, but I want to use limits because it's going to come up as a big cornerstone of calculus. So I just want to get you guys comfortable with it as early as possible, how to use limits. Alright, let's just plug in some points. So when x is 4, that's good because then you get 2 to the 0, which is 1, plus 2 is 3. Plug in x is 5, and we get, let's see, 2 to the 1, which is 2, plus 2 is 4. And then let's just plug in 0. Let's see, 2 to the minus 4 power, that's like 1 over 16 plus 2, so basically 2 essentially. And I can connect the dots, and there's my graph. All right, so let's look at some applications of exponential functions. One of them has to do with investing money. If you invest $8,000 in a stock, and that stock is increasing in value at 4%, so the stock is increasing in value of 4% per year. Okay, so the value of your investment is going to follow an exponential function. If something's increasing by a percent amount, it's growing exponentially. So the value of the investment, we can write a model for it, or a function, and the function's going to be, let's say, okay, f of x equals 8,000 is the initial investment amount, and it grows by 4%, so I times it by 1.04 to make it grow by 4%, and it does this every year. So for that to happen, then I want the years to be in the exponent spot, and that's our variable t. Let me change the way I wrote it to line up more with the problem. So the input is time, and the output is the amount of money you have. So let's use a of t for the function notation. It doesn't matter what you use, but I just want to use t for time and a for the amount of money you have after t years. All right, let's answer some questions about this. Question A, how much will your investment be worth in 5 years? How much moolah are we going to have in 5 years, right? All right, pause and think about how you would do it. Yep, you got it right. 5 is the year, so you put it in for the t, and you can just put this in your calculator, and you're going to get it's about $9,733. All right, easy enough. Just make sure that you can take the word problem and write the model. That's the really important part. Okay. Question B, when will your money double, right? When are we going to get that fat stacks? When is our money going to double up? So pause and ask yourself how you'd solve it. You got it right? Yep, I knew you would. I knew you would. So the amount of money for it to double was 16,000, and we just put that in for the amount, and then we're going to solve for the time, how long it's going to take. Now you could just graph this to find the solution, but if you don't have if you don't have Desmos with you, you can still solve it using logarithms. So we'll just divide by 8,000. So we get 2 equals 1.04 to the power of t. And we'll just use the really handy power of logs, which is you can take the log of either side and it's going to kick the exponent out in front and ready to be attacked and solved for. Just need to divide by my ln of 1.04. So the time is going to be ln2 over ln of 1.04, and we're going to get 17.7 years. So roughly 17 and a half years for your money to double. I recommend we find a different bank or a different stock to buy. Okay, 2 more applications, if you guys can hang with me here. Investing in money and it growing at a certain percent per year is exponential growth. But we also have exponential decay, and the example of that is something called radioactive decay. So the amount from the amount from 1 kilogram of plutonium, okay, which the radioactive isotope would be Pu to the 239. That's chemistry stuff. It's not that important for this problem, for the math, but just put it there anyways. The amount for 1 kilogram, the amount from 1 kilogram of plutonium that is left or remains after T years can be estimated using this exponential decay model. The amount of plutonium after T years is equal to 0.99997 to the power of T. So the question is, this tells you how much of 1 kilogram you have left. So you would take this and multiply about however many kilograms you started with to know how much is left. But let's just say, let's estimate the amount of plutonium that is remaining after 10,000 years. Okay, so we'll just solve it for 1 kilogram since that's what we have the formula for. So we want to know after 10,000 years how much is left. So we just put in 10,000 for the years and just put it in our calculator, and we're going to get about 0.74. So in other words, for every 1 kilogram of plutonium, 10,000 years later, about 3/4 of that 1 kilogram is left. And if you think about it, this is why nuclear waste is so hard to dispose, because plutonium is like a radioactive material, and I think it's a byproduct of nuclear waste. And it took 10,000 years, and you've only like 25% or a quarter of the amount has actually decayed. So 10,000 years. It's going to take a really long time for it to actually fully decay, and that's why nuclear waste is quite a problem. Okay, so the last exponential model example is going to be the logistic model, and you use this for modeling certain populations where you want to have an upper limit on the population amount, which makes sense because no population is going to grow forever. So this is a pretty good model for a population. The population of a bacteria in a certain beaker, boy, that's a word that you say if you want to sound real nerdy. Let me just check my beaker here. But anyway, the population of bacteria in the beaker at time t hours is given by the function population after time t equals 100,000 divided by 1 plus 50 e to the power of negative t divided by 2, where t is going to be our hours, and it's going to be greater than or equal to 0. So that we don't go back in time, at least for this problem. Find the upper limit of the bacteria population. How big is this bacteria colony going to grow to? How many bacteria? Well, if we think about it, the upper limit, that's going to be the limit as time goes to infinity. And we see this limit pop up again. Again, I just want you guys to get comfortable with the concept because it's going to be huge in calculus. All right, so what's going to happen to this function as time goes to infinity? Well, let's just focus on this part here that has the time in it, this 50e to the minus t over 2 power. Let's just pull that off to the side. This is a good strategy too, by the way, when you have a problem, just break it up into smaller pieces. Okay, so let's just look at this piece, 50e to the power of negative t over 2. Well, how do you rewrite that as positive exponents? Yep, you just bring it to the bottom and then it turns positive. So I have 50 over e to the power of t over 2. Now if I put in t is infinity, I'm going to have 50 over e to the huge number, which is going to be 50 over a really massive number, infinity, and that's going to go to 0. So that whole part that I've boxed in green goes to 0. So what's going to be left is 100,000 over 1 plus 0, which is 100,000. So 100,000 bacteria is our upper limit of population. And that kind of explains where that comes from in the logistic model. When you're using the logistic model for population, that number you put in the numerator is determined by the maximum population that you're going to have, the upper limit, if you will, of the population. So ponder that for a bit, and we'll see you in the next video. Thank you very much.